Hello, and welcome to the webinar on the 2024 updates to Chapter 4 of Volume 3. My name is Andrew Earls, and I'm one of the co-authors of Chapter 4, who is a senior stormwater engineer and hydrologist with Wright Water Engineers in Denver, Colorado. The purpose of the webinar today is to provide an overview of the updates to Chapter 4, which is the chapter in the Mile High Flood District's Urban Storm Drainage Criteria Manual that addresses treatment stormwater control measures, or SCMs. This is the first webinar in an on-demand webinar series related to updates to Chapter 4 of Volume 3. MHFD is also developing webinars related to the spreadsheet tools that are used to implement the criteria in Chapter 4. This webinar focuses on the front section of Chapter 4, which is critically important to properly applying the updated chapter to the design of stormwater control measures. Future webinars will go through updates to fact sheets and then delve into specific aspects of the chapter and criteria. Finally, we're planning to hold periodic office hours to allow users a chance to pose questions related to specific aspects of the chapter in an informal online setting. It's important to understand that the 2024 update to Chapter 4 was a stakeholder-driven process that was led by a multidisciplinary consultant team. We had nearly 200 stakeholders participate in listening sections, and we received and responded to more than 1,100 comments. The consultant team included engineers, hydrologists, landscape architects, and a geotechnical engineer, all with expertise in various aspects of SCM design and implementation. One of the major outcomes of this process was a shift to what we call a choose-your-own-adventure approach, which intends to provide designers with greater flexibility in how they combine various components of a stormwater control measure while still honoring the intent of the criteria. Other topics identified by stakeholders included additional guidance on treatment trains, greater emphasis on infiltration, and better site integration to provide value to the surrounding community. Today, we're going to focus on the front section of Chapter 4, starting with an overview of organizational administrative updates, and then discussing major topics in the front section that are shown on this slide. The basics of the four-step process still remain the same. The four-step process provides an integrated approach to stormwater management. Chapter 4 of Volume 3 focuses on the treat and slowly release step, but this step is influenced by and influences the other steps in the four-step process. Good design incorporates runoff reduction through the use of receiving pervious areas prior to treatment by other types of SCMs, and source controls in watersheds are always important for managing pollutant loads to the stormwater system. Properly designed SCMs that slowly release or infiltrate the water quality capture volume and excess urban runoff volume provide benefits for stream stability by minimizing the effects of hydromodification. In addition to the four-step process, we have tried to better integrate the 5 elements of watershed and stream health that we teach in MHFD's Stream Management Academy. These include hydrology and hydraulics, which we already addressed fairly well in this chapter, but also include geomorphology, vegetation, and community values. In the Chapter 4 update, we tried to provide improved information on community values to better integrate SCMs into the urban and suburban landscape. Stream landscape architecture provided excellent input on this topic, as well as guidance on vegetation. We consulted with a geotechnical engineer, Greg Monley of Wheeler and Associates, on subsurface exploration to provide better guidance for determining whether or not a site is suitable for infiltration-based SCMs. Some of the biggest changes to Chapter 4 are organizational. We formally had a cookbook approach that included a lot of repetition in the fact sheets. The new organization allows engineers to create their own combinations of SCM components, customized to a project site. We still have fact sheets, but for the topics common to multiple SCMs, for example, inflow features or underdrains, the fact sheets refer to the front section. This requires the user to be familiar with both the front section and the fact sheet, as well as other chapters in the MHFD manual. The front section provides common components, and the fact sheets provide detailed design procedures that reference portions of the front section for guidance on designing various SCM components. We've also introduced some new terms. We have the WQE, which is the Water Quality Event, a rainfall event with a depth of 0.6 inches. We have the water quality peak flow, the WQPF, which is the flow resulting from the WQE. Finally, we're now using the term stormwater control measure as opposed to the previous term that we used, which was best management practice, or BMP. This is a flowchart that explains how Chapter 4 is to be used in conjunction with the fact sheets and other sections of the MHFD manual to design SCMs. I'm going to briefly walk through these steps, but the main point of this slide is to explain that there are different sections of the manual that you will need to use to design an SCM, and that starts with selection of the SCM type, which is rooted in chapters 1 through 3 of Volume 3, and also in some sections of Chapter 4, including community values. It includes calculation of design volumes. The guidance for that is provided in Chapter 3 of Volume 3 or Chapter 4 of Volume 3, as well as in Chapter 12 of Volume 2, which is the storage chapter that includes guidance on the EURV and 100-year storage volume. The SCM design process includes applying workbooks, including the SCM design workbook and potentially MHFD detention for full spectrum detention facilities. And it includes evaluation of the appropriate infiltration or filtration section to be used if you're able to use a filtration or infiltration-based BMP. Several sections of Chapter 5 or 4 in the front sections, including Section 5 and Section 6, can be used to design SCM components, and Section 7 of Chapter 4 can be used to provide guidance and information on soils, vegetation, and irrigation. And of course, no design of an SCM is complete without maintenance considerations, and maintenance is addressed in Chapter 6 of Volume 3. So, in other words, to design an SCM, there are a number of different chapters and sections of Volume 3 and even other volumes of the Mile High Flood Districts Manual that will need to be used. The 2024 update of Chapter 4 emphasizes community values in the planning, design, and construction of SCMs. As I mentioned earlier, Stream Landscape Architecture provided excellent input in this section on how to make SCMs a more functional part of urban and suburban landscapes that provide benefits beyond just stormwater treatment. SCMs are beneficial for protection of public health, safety, and welfare, and are also required by local governments that are MS4 permittees. However, these types of facilities can also have significant visual and experiential impacts on their surroundings, and that's why these community values are important. The impacts on the surrounding environment can be negative or positive depending on planning and design factors, including selecting the appropriate types of SCMs for the site, proper siting of features, design details, materials, and finishes of major elements, grading and landforms, vegetation, scale, and the overall user experience. As SCMs become more commonplace in urban and suburban settings, it's important to understand the influence that these features have in the landscape and how important good design is to have positive outcome. It's important to consider how our investments in water quality treatment can provide values to the community beyond just the primary treatment objectives. Another topic that we expanded on in Chapter 4 is site assessment methods. The approach suggested is a multi-phase approach with an increasing level of detail as you move through the different steps. So site assessment really begins with a desktop assessment and gathering of relevant information on hydrology, soils, groundwater, and other factors that may affect the types of SCMs chosen for a site. This phase would also typically include a site visit to document existing site conditions, and it would also include checking different state and local databases to see if there's any suspected contamination on the site. The initial site assessment is really intended to identify opportunities for runoff reduction practices and to provide preliminary information on the suitability of the site for different types of infiltration-based SCMs. If it appears that the site may be suitable for infiltration or filtration-based SCMs, additional subsurface exploration is then conducted, and that could include an initial assessment with boreholes or pits, to test out the permeability of the subsurface following guidelines from the state of Michigan's LID guidance. Typically, we like to have at least one boring for at least 160,000 square feet of the development area, but no less than 2 total borings for this initial assessment. And then you also could have final design, which would be more detailed testing using an infiltrometer, such as a modified Philip Dunn or NRCS double ring infiltrometer. You must be sure that these evaluations are at the proper elevations for evaluating the SCM subgrade, or else you're going to get results that don't really mean a whole lot. And for this reason, we typically say that for the initial assessment, borings or pits should extend at least 5 feet into the subgrade, and deeper in some cases where you have a lot of cut on your site. Our update to Chapter 4 uses a 2-stage subsurface investigation process. As I mentioned before, we have the preliminary investigation, which could be test pits or test holes. And then what I'm showing in this slide really is the kind of equipment we would use for a final design investigation. And this is showing infiltration measurements using what's called a modified Philip Dunn infiltrometer. There's some other simplified methods, such as TurfTech infiltrometers or mini double ring infiltrometers, that are good for assessing relative infiltration rates, but they are not as accurate as a modified Philip Dunn or a double ring infiltrometer for determining quantitative infiltration rates, and therefore one of the quantitative methods should be used for the final assessment. This flowchart is really an illustration that guides you through the site assessment process and the selection of the different types of SCMs that would be used. In the past, we've really set a high bar for infiltration rates, and in some ways this has actually been unrealistically high for full and partial infiltration systems. Over the past decade, we've really found that these types of systems can function quite well as long as the long-term saturated infiltration rate is on the order of 1 inch per hour or more. And this chart is really intended to guide engineers through the site assessment and SCM design procedures with really an order of preference for first looking at runoff reduction measures, then considering lined SCMs, followed by looking at what if we can't do a full infiltration section or a partial infiltration section or a lined infiltration section, then perhaps we would consider what types of sedimentation-based SCMs like ponds or dry ponds that we would use. But we really want the users to work through this flowchart of first considering runoff reduction, then considering full infiltration systems, then partial, then no infiltration, and then finally considering ponds after those options have been exhausted. This slide contains a risk matrix that includes some guidance for how to interpret the results of subsurface exploration for determining what type of infiltration or filtration section would work at a site. And one of the questions you may have is, well, what do we mean by risks? Well, risks are really defined by the user, but they can include a lot of things. They could include poorly infiltrating soils that have risks of leading to standing water or declined performance of the SCM. Nuisance issues could be risks, mosquito vectors, shrink and swell soils, or the presence of nearby building foundations or adjacent roads and utilities. Those are all potential risks that you could encounter. And the intent of this chart is to really explain how the varying levels of risk relate to different options for infiltration systems, from a full infiltration system to a no infiltration system, to some extremes where it may even be best to just avoid trying to do any type of an infiltration or filtration system. So this is really a risk-based approach that allows users to select the right type of infiltration or filtration section to use based on the risks that they identify on the site from their site investigations and subsurface exploration. The 2024 update also includes changes to the standard filtration and infiltration systems. We still have the basic, full, partial, and no infiltration sections, but we've refined some of the details. For example, we have made the filter sand layer a bit smaller using a trapezoidal shape above the underdrain trench. Previously, that extended across the entire bottom of the SCM. We've also provided updated guidance on non-woven geotextiles to be installed below and above liners to provide cushioning. We have new guidance on liner and liner penetrations and new details. And we also have updated guidance on underdrain sizing. And these details, the section details for the partial infiltration, the full infiltration, and no infiltration sections are really the core of infiltration or filtration SCM design. Once you've selected the type of SCM, then the choose your own adventure begins with looking at different types of options for inlets and outlets and landscaping. And one of the main goals of the SCM inflow features section was to provide a range of options for sheet flow and concentrated flow conditions, because you could really run into any of those in urban areas. And while sheet flow conditions are desirable in many urban areas, runoff is concentrated, and therefore we wanted to provide options for both types of flows, as well as different ways that you can actually turn concentrated flows into shallow sheet flows using processes like level spreaders. And this table that I'm showing on this slide provides various types of inflows that are compatible with different types of SCMs. This is extremely important because some types of stormwater control measures, like RPAs, require sheet flow for effective hydrologic and water quality treatment, while other types of SCMs are better able to accommodate concentrated flows with proper energy dissipation at points of inflow. On this slide, I'm showing you a few different examples of renderings that Stream created, showing different inflow configurations. You've got a slotted curb inlet that you're showing kind of on the left that also has a sediment pad. That's the type of inlet that could be used for many types of SCMs like bioretention or sand filters. And we also have a good illustration of a level spreader on the right-hand side. A lot of the updates that we provided related to level spreaders were taken from research by Dr. Bill Hunt of NC State University, who's been studying the design and performance of level spreaders for more than a decade. And the sheet flow info features are particularly important because we've really placed an emphasis in this updated Chapter 4 on receiving pervious areas and runoff reduction, and sheet flow is really the key to making those work properly. The inflow features section also includes examples of forebays and forebay sizing criteria. For smaller SCMs that drain relatively small amounts of impervious area, a concrete sediment pad, like we showed on the last slide, can be a simple and effective choice for a forebay. At that scale, infiltration or filtration-based SCMs that infiltrate runoff are really handy because you can release the flows through an underdrain and you avoid a lot of the problems that you can have with small orifice sizes for the pond-type SCMs when you have small drainage areas. When you get to larger watersheds, forebays are typically sized to provide a 4 to 5 minute drain time for a volume equivalent to about 1% of the WQCV. The SCM outflow features section is similar to the inflow section in that it identifies different outlet types that are applicable to different types of SCMs. And selecting the right type of outlet is also critical because a poorly functioning outlet can lead to a lot of problems, from standing water to mosquitoes to impacts to vegetation to diminished performance. And a lot of ponds really have problems because of small orifices that have to be protected with well screen. When you're in the territory of having orifices with small diameters that need to be protected by well screen, I would strongly encourage you to consider alternative types of SCMs that rely on filtration or infiltration, like bioretention or sand filters. Because even if you protect small orifices with well screen, the well screen will become a long-term maintenance issue and has high potential for clogging. And when you can make the orifices large enough, typically 2 inches or greater, you can then use bar grading instead of well screen, and that can significantly help reduce the clogging potential of outlets. These two renderings are a couple of examples of outlet structures that we're showing here. Actually, one rendering and one photo in this one, but we've created quite a few renderings. The rendering on the right is really showing the type of outlet that could be used for a bioretention facility. It's an orifice-controlled outlet for the WQCV. The larger flows would spill over the grate and flow into the outlet pipe. And the photograph on the right is from the River Run bioretention area, which has a similar type of outlet design. And this same type of outlet could also apply to a sand filter. We've created a number of similar details for permeable pavement systems, and Muller Engineering did a whole lot of work updating outlet structure details for extended dry basins. Green infrastructure is not really green without healthy vegetation, and we all know that vegetation helps to stabilize soils by protecting from raindrop impact, intercepting rainfall, anchoring the soil with roots, and promoting infiltration. We also know that vegetation helps to mitigate urban heat island effects and contributes to visual interest and community value. It's important that vegetation is adapted to a range of hydrologic conditions that will be encountered within an SCM, because you can have different portions of an SCM that will have different hydro periods, and different vegetation will do well depending on the hydro period that it's exposed to. Of course, healthy soil is really a precursor to healthy vegetation, and where we've seen the greatest struggles with establishing vegetation typically are in areas that do not have adequate topsoil. And in that regard, we have increased the recommended minimum depth of topsoil in Chapter 4 from 4 inches to 6 inches. And we also, in a number of places, reference the MHFD topsoil guidance document, which is an excellent resource for either creating healthy topsoils or amending soils to create healthy topsoil. And last but not least is irrigation, which is a topic that cannot be neglected even when you're designing with native species. For native installations, you may only need irrigation during the establishment period, but it could also be required during future extended droughts. And without at least temporary irrigation, many vegetated SCMs are likely to struggle with establishing healthy and dense vegetation, which is why we call for temporary irrigation. And this, of course, is something that is likely to be exacerbated by future changes in climate. Finally, the 2024 update to Chapter 4 includes update to fact sheets. We have a new fact sheet on receiving pervious areas that combines and updates previous guidance on buffers and swales. We have a new fact sheet on rooftop systems, which has expanded on the green roof criteria, but now also includes a blue roof, which is essentially a green roof without the vegetation. We have an updated bioretention fact sheet that has a new media mixture with increased organic content for better supportive vegetation while still providing effective infiltration. We've updated the sand filter fact sheet. There were not a lot of major changes to the criteria in this fact sheet, but we've incorporated some new graphics. We made some major changes to the permeable pavements fact sheet, and we significantly expanded the guidance with some great input from Curtis Kostecki of Creative Civil, and we've included a lot of new details related to permeable pavements. I mentioned a minute ago that Muller Engineering, Jim Williman, and his colleague Tracy Bolger conducted a real overhaul of the EDB criteria, including updated guidance on selection and sizing based on the impervious area draining to the EDB, a lot of new details, and improved guidance on when to use bar grading versus well screen. We have combined the retention pond and constructed wetland pond fact sheets into a single fact sheet. These are somewhat less commonly used SCMs due to water rights, but they have a lot of design criteria in common. And finally, we really overhauled the MTD fact sheet, the manufactured treatment device fact sheet, which has really categorized SCMs based on their treatment processes. We've also specified that hydrodynamic separators are really only acceptable for pretreatment, and we provided guidance on how to use the WQE and the WQPF, remember the water quality peak flow rate, for sizing flow-through based MTDs. And that brings us to the end of the webinar. Thank you for attending today. If you're interested in accessing Chapter 4 of Volume 3, the link at the bottom of this slide will take you to MHFD's website where you can download a PDF. Thank you for attending.